The first section in Chapter 3 is about graphing our three basic functions. The three functions we have in Section 1 are exponentials, logs, and logistic functions. Logistic functions are probably brand new to you, although you've experienced exponentials and logs before. So the first graph we're going to look at is exponential growth and decay graphs. The thing that you should certainly know about an exponential growth and decay graph is you should know that they always, unless they have a vertical shift, they're always going to have an asymptote at y equals 0. They're going to have a horizontal asymptote as either as x goes to infinity, our function is going to go to 0, or, as in this case, as x goes to negative infinity, our function will go to 0. The other thing you should know about an exponential graph is that the a value is the initial amount. It is also the y-intercept. So you're going to find that a value on your graph at 0, a. So this would be 0, a on both of these two graphs. The a value determines how far up on the y-axis your graph starts. The b value is going to be either a decay or a growth factor. And the way you can tell if it's decay or growth is you can say, well, is b greater than 1? In which case, every time we multiply by that b, our graph is going to go shooting upwards. Or is b less than 1, in which case we'd be multiplying by a fraction or a decimal, and our graph would get smaller and smaller. This is called decay, and this is called growth. So on your note sheet, you have an example of an exponential function, 2 times 3 to the x, which means that our y-intercept is going to be 2. That's the a value is 2. And then our growth factor is going to be 3, which means if I increase x by 1, I'm going to multiply by 3. So that means if I go from 0 to 1, I'm actually going to multiply 2 times 3 and get 6. If I went from 0 to negative 1, I would divide by 3, so I would get 2/3. Each point along the graph, every time I move over one x coordinate, I'm going to multiply by another 3. So this graph gets really big really fast. This is going to be exponential growth because 3 is bigger than 1. The domain for this graph is going to be all real numbers. There is no domain restriction on exponential functions. The range, if I think bottom to top, we're going to start really close to 0 and we're going to go up towards infinity. The y-intercept is going to be 0, 2, and we can see that in our equation as the very first thing. As x goes towards infinity, our graph is shooting up towards infinity. But as x goes towards negative infinity, our graph is leveling off towards 0. The equation for the asymptote, because this graph has a limit of 0, the asymptote equation is y equals 0. If I want to graph that asymptote, I would do a dotted line on the x-axis. This is an example of a growth function because b is 3 and 3 is bigger than 1. So our next example is an example of a decay equation, and I'll show you that. So our y-intercept is going to be 4 because we can see that right there. And then our multiplier is going to be a half. So every time I move over 1, I'm going to multiply by a half. So if I move over 1, I'm going to do 4 times a half, which would be 2. If I move over another one, it would be 2 times a half, which would be 1. If I move over another one, it's going to be 1 times a half, which would be a half. And so our equation, our graph, looks like this. The domain, there is no domain restriction. The range is going to be from 0 to infinity. The y-intercept is going to be 0, 4. As x goes towards infinity, this graph is leveling off to 0. As x goes towards negative infinity, this graph is shooting up towards infinity. The asymptote equation is going to be y equals 0 because that is one of our limits, is a number. And this is an example of decay because b is less than 1 or b is equal to a half. The other kind of graph we're going to do, one of the other kinds, is logistic. Logistic graphs are different from exponential because they have 2 asymptotes. In the beginning, the graph looks a lot like an exponential, and then it starts leveling off. So the leveling off value is going to be y equals c. It's going to be our carrying capacity, that's called. Or our limit to growth. And as x goes towards infinity for this function, our function is going to go towards that carrying capacity. As x goes towards negative infinity, our function is going to go towards 0. So it actually has a second asymptote at y equals 0. This point right here is 0 for the x-coordinate, and it's f of 0. And I want you to put a little star next to this because this feels like it should be a, but it's not a. You have to do some math in order to figure out what the y-intercept is. We're going to do an example. So for this example, we have a carrying capacity or limit to growth of 8. So that means that we have an asymptote of y equals 8. So I'm going to start by drawing that. We also have an asymptote because it's a logistic equation of y equals 0. The domain, there is no domain restriction, so the domain is going to be negative infinity to infinity, but the range is stuck between 0 and 8. Oops, that should be an 8, not an infinity, sorry. Now for the y-intercept, we have to do some math, so we're going to go ahead and do that. We're going to plug in 0, and we get 8 times 8 over 1 plus 3 times 0.5 to the 0 power. Anything to the 0 power is 1, so we have 8 over 1 plus 3. Since 1 plus 3 is 4, this is going to be 2. Our y-intercept is going to be 0, 2, right here. The limit to growth we talked about is 8, and the limit as x goes towards infinity, so to the right, is going to be 8. As x goes towards negative infinity, the limit is going to be 0. The asymptote equations are y equals 0 and y equals 8. And when we sketch our graph, what we're going to do is we're going to make it look like exponential growth, and then we're going to level off towards our asymptote. The only point that I will be checking that's on your graph will be your y-intercept. I'll be checking for the y-intercept, and then I'll be checking to see that you behave appropriately towards your asymptotes. So that is a logistic graph. The final graph are log graphs. Log graphs are inverses of exponential graphs. So the inverse of log base a of x is going to be a to the x. And what that means is that any ordered pair that's on F inverse is going to be flip-flopped and be on log A. It also means that the log graph is going to be a reflection across y equals x of this inverse graph. Since this b value is 1, this graph is going to have a point here, and it would look like that. So that would be the growth graph, the exponential graph. The thing you need to know about log graphs is that this point right here is going to be 1, 0, unless you've done any shifting. And the other thing you should know about log graphs, which are not these ones, that's the one that's shown there. The other thing you should know about log graphs is that you are going to have an asymptote at x equals 0. This is the only graph we have so far with an asymptote that is vertical. This graph is going to go out towards infinity as x goes towards infinity. I'll do an example of a log graph. Okay, so the domain of the log graph, because it stops at the x-axis, the domain is going to be from 0 to infinity. I can't use negative numbers in a log function. The range, though, is going to be all real numbers, so negative infinity to infinity. The x-intercept for a log graph, as long as you have no translations, is always going to be 1, 0. So this will be my x-intercept. For this particular log function, the inverse is going to be 2 to the x, because our base is 2. So what that means is, if I find an x coordinate on the inverse, so if I say, well, what if I use x equals 0 on the inverse? That would be 1. So that means that on the original function, I have the ordered pair 1, 0. If I plug in x equals 1, 2 to the 1 is 2. So on the inverse, I have 2, 1. So that means that this point is on my graph. If x is 2, the inverse would be 2 to the 2, which is 4. That means that 4, 2 is on log base 2. So if I use a negative 1 for an exponent, that means that I have 2 to the negative 1, which is a half. And that means that x equals a half is on the graph at negative 1. So I think you can see that basic shape. It looks like this. As x goes towards infinity, this graph is going up towards infinity. As x goes towards 0 from the positive direction, this graph is shooting down towards negative infinity. The log graph has a vertical asymptote, so that asymptote equation is going to be x equals 0. So what you should be responsible for is drawing the basic shape of a log, a logistic, and an exponential function. Good luck. Let me know if you have questions. Thank you. Bye.